Thank you, John. I perhaps should tell you how I almost succeeded in delaying the determination of the structure of the first globular protein by a year or two. I was in my laboratory in Pasadena, and a young man in uniform, a flight lieutenant, came in who had just arrived from Burma, perhaps, or some place down there, about 1945, saying that he was on his way back to England and was going to work on determining the crystal structure of a protein, a globular protein molecule by X-ray diffraction. I said, well, that's nonsense. You've never determined the structure of any crystal. You'd better work on something simple, you know, with only a half a dozen atoms in the molecule, and get your PhD degree, and by that time you'll have enough experience to attack. John Kendrew was his name. He ignored my advice. So the first, I think it's right, the first crystal whose structure he attempted to determine by X-ray diffraction was myoglobin. And he succeeded. The next speaker, now I'll introduce Professor Hodgkin, who determined the structure of penicillin, not only determined its crystal structure, but also discovered the correct chemical formula for it with a four-membered ring that the chemists, great chemists, had been unable to accept, and who worked for long periods of time on the structure of insulin. Professor Hodgkin.
Thank you very much. I hadn't meant to go back so far, but of course I should say that one of the first forays I ever calculated in my life was the one of insulin, and that Patterson was very pleased to see it. And I wish I'd put in one of the last slides that I had made in memory of Patterson, which is the Patterson as it is today of a calculated from all the reflections observed for insulin of the same section. But it's still a problem, I should say, from that slide to solve a protein crystal from any data set existing in this world at present. I first met proteins myself by the accident that Glenn Millikan brought to Cambridge, to Burnell, a tube full of very beautiful pepsin crystals grown by John Philpott. And Burnell discovered that these could only give X-ray reflections if they were kept in their mother liquor, and so started off the technique for mounting crystals that goes on persisting, and I think to some extent anyway necessarily, of keeping crystals, protein crystals, still immersed in their mother liquor. Though in the early days we were always believed that they should have plenty around them, which caused a certain amount of problems with their swimming about in case they got distorted by surface tension effects, which at the latest developments seem to show is quite unimportant. I followed the taking of the first pepsin crystals with taking photographs of insulin which again was given me accidentally, 10 milligrams of it by Sir Robert Robinson. And I thought, I let them dry, which was stupid, and so got a limited set of reflections, but they were rather well-defined kind of crystals, so they gave a good dry diffraction pattern from which a first exact molecular weight, not very exact actually, for various reasons, of a protein could be calculated. The asymmetric unit was of the order of 12,000, and Bernal wrote straight away to suggest in a letter that I have a copy of here, zinc 0.05 to cadmium 0.75. You don't have to say what you mean by these words. The text clearly meant you should make a cadmium derivative, or there is a cadmium derivative of this protein. With zinc changed to cadmium, you might be able to get some phases and do the correct calculation of the electron density. The letter ends, I will send you some of the cadmium stuff from Cambridge. And he got it from Chibnall, who was working on insulin at the time. Well, I never succeeded in growing large crystals of the cadmium stuff, comparable with the zinc ones. I think because at that time, I think just the preparation was too impure. And also, I'm afraid I was too unbelieving. I didn't believe the change from zinc to cadmium was enough to give me phase angles with an asymmetric unit of the size of 12,000. I thought I hadn't solved any structure at all. I was less courageous, if you might like it, than John Kendrew. I thought I'd better begin with some small molecules to test out the idea of using heavy atoms and isomorphous replacement on the possible calculation of electron density maps. And it was great luck that one of these small molecules that I did work on was penicillin, just the right size for a beginner. But the curious thing to me when I think of it now, I mean, all the calculations that mattered were done with Beavers-Lipson strips, or all the intensity measurements with just this method that John Kendrew described of looking at the little of eye estimation. The sizes of the units at the end punched cards were developed by John Comrie and gave us the possibility of doing a three-dimensional electron density map. Nobody nowadays does three-dimensional electron density maps of anything of the size of penicillin. Jumped straight from the computer to the answer, but it still is used, of course, for proteins. And yes, I think we need to develop some of the old techniques or rethink again the techniques that are used today. What I really meant to talk about today was, curiously enough, points that worry me about the techniques today compared with the old ones. People discover protein structures so quickly, and I can't believe they have time to look at every individual residue as carefully as they should, because the whole mass of a protein structure conceals so many possible differences within it from the point that show up differently in electron density maps. So I put up, first of all, a little thing that happened to us in the course of the insulin investigation, which in the end we began very late after myoglobin and hemoglobin had been solved, and took a long time over, not getting any heavy atoms quite as good, any heavy atom derivatives quite as good as those used in the first myoglobin and hemoglobin syntheses. So that our first electron density map had a lot of imperfections. And when the structure had been roughly solved, we started refining it by the usual process of assigning coordinates within the framework of the map, and calculating by least squares the best fits for the observed intensities from those coordinates, then calculating another map, and so on. And because we had various different ideas amongst any group of, by now, about 8 or 9 people, numbers growing with the complexity of structures, the group split essentially into 2. Neil Isaacs and David Sayre took over at IBM, and the rest of us stayed behind at Oxford, particularly Guy and Eleanor Dodson and Tom Blundell. And they both wound the handles and produced results that they thought should be reasonably in agreement. They left out the inner reflections, which I never believed in doing. And the others quoted 17% not being allowed to leave out the inner reflections. They came through with essentially very well good agreement with the actual distribution of the atoms, except for about 8 residues where they had quite different conformations and distributions. So then we did a difference map in which we put in the coefficients for all of the atoms as found, except the 8 in each case, and they only believed in their own determinations of structure, so they had the completely different set of atomic positions. Well, I said in very near agreement, but just these ones left out. Now, the first slide I have to show is just one illustrating what happened then. On the left-hand side, there's the 2 different positions suggested for the, well, one actually was a disordered position set, so there are more positions than that of the atoms. On the right-hand side, the 2 Fouriers, and the 2 Fouriers give the correct answers. They give the same correct answer, although they are different, of course, because the coefficients all the way through are different. I don't know why they had these particular theories had these names, but the right-hand side is the IBM set and the left-hand side is the Oxford set. We then, after this, checked our whole structure by a process devised by Eleanor Dodson, in which 1/8 of the whole map was removed at a time, and the electron density within it calculated in terms of the phases of the other 7/8. So you ended up with the structure of the crystal, in which, seen in this difference map, with no atoms placed. So I'll just show very quickly, following them, but the next slide. First, a little bit of the structure from the first map we calculated at all at 2.8 angstroms. Then, in the next slide, the 1/8 removed map, which shows exactly the same patterns, and the only thing that's perhaps noticeable to point out about it
can hear you in the other auditorium.
Yes, yes, right, sure. Now, for example, the thing that hasn't got an atom on it here is a water molecule. The other points mark the atoms as finally they appeared in the next slide. That's the Fourier map, F-observed map at 1.5 angstroms with the atoms as they occurred. But you see they were all there at the very beginning. Now the next slide shows the end of the chains on the outside of the molecule. Those first well-defined atoms are on the inside of the crystal, the hexamer. And here is the end of one chain, the A chain. And you see, not all of the atoms are defined. Here at the end of the B chain, there's only one atom really marked by electron density. The next slide shows the 1/8 removed map. And they've all occurred. You see, the phasing of this map is much better than the initial heavy atom one. You now have got defined the end of the B chain and the beginning of the A chain. On the next slide, the end of the story, just the same essential pattern. So I have a strong believer in doing something like this with most protein structures, unless you have got really good phasing to begin with. There are just little things that go astray in different parts of a crystal structure, of the size of a protein crystal structure, although insulin was a small protein. Could I have the next slide, please? This is just an illustration of the structure as seen of the unit cell with all the atoms in the protein molecule projected down the threefold axis of the crystal, with the zinc ions that lie in the crystal that caused Bernal's first letter lying along the threefold axis. This represents 6 molecules packed together, first in a dimer. Then we break this dimer apart. You see 2 different molecules, looking molecules, and then the chains, the A and the B chains of insulin. The A chain smaller, the B chain larger. And the thing you notice is that they appear obviously very much the same. They have the same chemical structure, but they appear different in this projection, although roughly there's a 2-fold axis down this line. Well, it's rather a puzzle what this difference is and what it's due to. And we are rather pleased to have another complete determination of the crystal structure of insulin, which we can check the identity. And this was the structure analysis carried out in China at the time of the Cultural Revolution. we had started, of course, rather long before they started, and in the early stages of cooperation between China and ourselves in 1959, they had told me they were synthesizing insulin in China, which they did, and I suggested they should synthesize a heavy atom into the chain, which they did, and which we did. And it was all no use at all, because the heavy atom derivative I suggested didn't crystallize. And however, they started away themselves, particularly under the direction of Liang Dongchai, who many people probably here know, to work and find much better derivatives than we actually found. And we finally compared our two maps after some hesitation in 1972 at the time of the Japanese International Congress. I stopped at China on my way to Japan. So the next slide shows you our first comparison. And here is the inner part of our structure, part of which you've seen already, which was easily interpretable in terms of Fred Sanger's sequence of insulin. These are three of the side chains, and in the center of this gap here is the zinc. In the next slide of the Chinese comparable region shows is cut at a slightly different level and has the zinc in it. We've both gone on from this to extend the data and do the calculations that I've shown before. And the next slide shows our map, a bit of our map at 1.5 angstrom resolution, which shows you that most of the atoms are clearly distinct from one another, and these are the water molecules with the same relative density. Now, we go on comparing our maps. So last time I was in China, at the time of many of others here also went, we exchanged maps and left behind one with them, and they gave us their latest one. And it's very, very interesting, because they have extended their data further than we have. They've extended it almost to about 1.2 angstroms, is that one, yes. And now when we put them, and they've had David Stewart to guide them to cut the intervals in the Fourier, the three-dimensional Fourier, at the same levels as we have, so that we should be seeing exactly the same thing instead of the original comparison. And here you see how close I've chosen two lines that are supposed to be the same absolute intensity. The black line is, blue line is the Oxford map, the red line is the Peking map, and you can see that the lines really fall, in many cases, extremely close together, although the numbers of reflections within the maps is quite different. And this is, of course, because I've left out ever so many, because what you find is these two, which should have the same electron density approximately, are the same, but the Chinese ones go on very much higher than the Oxford ones. Most of the far-out reflections contributing, as you'd expect, to the protein, giving you the possibility of fixing the protein positions much better. And so that they're well worth having. Now the next two slides, could I have them show the same region that we had before? That's to say the histidine attached to the zinc atom. And you can see now the electron density has been cut in the other direction, and the individual atoms are very well resolved. This is an electron density map calculated from data extending to 1 angstrom in Japan by the Sakabis. The next slide shows that this map shows the hydrogen positions as quite well-marked peaks, though not very accurately placed. This map, I should say that this illustrates what I said a moment ago, that some parts of the structure are very, very well defined, particularly the region all around zinc ions, which you'd expect. But right at the edges of the map, the definition is not so good, so that I can't say that that definition persists the whole way through the Japanese map, but still most of the structures is directly comparable. Now the next slide just shows the representatives of the working groups in comparing the maps. And you can see we've got them all out and are putting them on light boxes on top of one another. And we have at this side Liangdong Chai and one of the Wangs from China, Nori Sakabi from Japan in the middle with Kiwako there, and it's Tom Blundell who's hidden behind, I'm sorry to say myself. But, it's been very interesting and instructive watching the whole different investigations develop. There are all sorts of points that are a problem with in the insulin structure, and perhaps the worst, the most difficult one is this: why are the two molecules? Why are the two such different molecules in the unit cell in this structure, which we all know because both three groups have found it. Now the next slide just illustrates the differences. Here are two molecules of insulin, seen now perpendicular to the threefold axis. And you can see that the ends of the B chains are different, that in one case the group sticks up much higher at the end than the other. In fact, this was our first trouble in China, that when we compared the maps the first time, I putting our map from England on top of their map from China, they were different. And then I suddenly remembered that Guy had said when he saw a model of their structure, a photograph sent across, they've got it upside down, turned it upside down. Luckily, I had mine on tracing paper, and they fitted at least quite reasonably, as you saw they ought to from the photographs. Why this occurs, we think, and we need some advice from Linus over this, is that in the packing of the molecules in this crystal, one packs one hexamer on top of another in a simple way, because there are these projecting groups on the top of the hexamer surface. And they lock into one another. But they're locking into one another brings them into such a position, could I have the next slide, please, that the histidines are locked together. Now this would lock together unless something happened. This something that happens is at the beginning of the helix of the A chain of insulin turns on into a different position over the disulfide containing chain below it. Now you can see this is looking down an alpha helix. But looking down on the other molecule, you've got a different projection. It seems that the helix just turns around one bond and all the residues stay with much the same conformation and make the same contacts. Here's a B4, A4, sorry, glutamic acid turning down towards the end of the chain. Over here, here it is in the same sort of conformation. Only one has a totally different conformation, the isoleucine, which is here and turns round into a different position here. And the next slide shows, the fact that these two histidines fall on top of one another, would fall on top of one another if one didn't turn aside and change the relative packing of the beginning of the A chains. The next slide just shows what this surface is. This is the surface, the top surface and the bottom surface of the hexamer. And here are the histidines nicely moved apart from one another, but into different positions. One has moved, and so the whole beginning of the A chain is different, though the rest is left the same. Now the next slide shows things that one has to remember. These are very well-defined groups. In fact, they're all the non-polar groups, all the invariant leucine of the molecule, all the and one of the disulfide bonds, the internal disulfide bond, packed together in a sphere within 6 angstroms of the sort of mass center of the molecule. This is of one chain, the chain we call molecule 1. Now the next slide shows molecule 2, and now when you look at the leucine in this one, all of these are quite nicely arranged, but in a somewhat different arrangement, and the leucine has very low relative electron density running down here. So that the low electron density, which of course gives you calculated low Bs, does not here represent necessarily a changed vibration movement, but this tracking round to a new position in the crystal, which it can't quite get to properly to fit in, as you might say, it being the unnatural kind of position to have. I should go on. I think the next slide gives the whole crystal structure. And I might show this also on the overhead screen. We have left out so far what happened to the water molecules, what happens to the spaces in the crystal. I first of all just have here all the way around. Sorry, yeah, yes, you just lift it off. They touch, it's body-centered, cubic, close packed approximately, and they touch on every side. But of course this traps great spaces between them, which now, if we switch over, we can see are filled with water. This is, yes, sorry, I was right. I was looking at the wrong one. You can see there are channels right the way down the center of the crystal and down the threefold screw axis from top to the bottom, and then a circle of a belt of water molecules coming out of the threefold screws, wrapping round each hexamer, and lines across, and streams across. Dash. That's all I do. Streams across the join so that water is continuous through the crystal. Now, I'll just show you quickly on the next 5 slides what the water molecules look like in water. The inner circle, as you might guess, are nicely packed, tetrahedral, and so on. Above them, there's a much larger area of water between the hexamers on the outside. Next one, please. You just have to see that they stretch out from the center of the group in somewhat disorderly chains, ending by being close to being bonded to the peptide chains of the molecule. And the next one, these are the rather thinner layers, and they have got into quite reasonable zigzag order, but still connected with the chains. And the last lot is really very much more disorderly, but still you can trace peaks that are rather in a rather zigzag kind of arrangement to one another within the region. Now, I wanted to mention one other subject, so I must do this rather quickly. And this is, of course, that this is one crystal structure. But can I have the next slide, please? When Schlitt-Krull was making slow-acting insulins, he made a number of different crystals by doing experiments of a rough kind, dropping the cresol, phenol into the solutions, and from this very large crystals came out, or adding 4 more zinc. These rhombohedra, very much like our different original rhombohedra, came out. And somehow we started slowly making measurements on all of these, and new things began to happen. Next. Nice. Yes, sorry. Next slide, please. God. One of those slides, I'm sorry that one should be a sticking one. It's not a very old one at all. It's one of cubic crystals, and it was grown by Anita Bentley, who is here, and it was just discovered that it crystallized on the alkaline side of the point. The crystals on the first side were very small rhombic dodecahedra. By adding different habit-changing hydrocarbons, Anita has grown enormous flat cubic crystals on the next slide, the structure quite different from our ordinary one. These two slides could come quickly, one after another. I've got one more structure I have to go through. This is a cubic one with rather beautiful structure with the molecules stretched along the three cubic axes. And this is one line of dimers going down. And the dimer here is regular on the next slide. You can see the top and the bottom, the B chain stretched out, running into an alpha helix, then stretching out, and the A chain curled up into the gap. Okay, now another crystals. Too bad. I have to give you this last one, Linus. This is a structure in which we we found that in the four-zinc crystals, unexpectedly, the B chain had changed at the other end, and instead of being extended, was coiled into an alpha helix. And the crystal consisted of three changed molecules over there, and three unchanged molecules. That's the four-zinc one. Now the next one is another, the crystals grew very large, the moleculic ones, with phenol in them. And there, it was recently discovered, both at Buffalo and with us, that there were 6 chains, all the same, with alpha helices at the beginning. And why, we don't know. They also occur in one of the other crystals. Now, these ones that grow with phenol, the phenol actually reacts with them. The last slide, or last slide, but one, that's to say it's hydrogen bonded to a bit of the chain that is exposed when the chain coils into an alpha helix. But there doesn't seem to be any reason why it should be the phenol that causes this change, because it also occurs in the other one. And I think there is one slide at the end, which is, oh no, that's another thing that happens in crystals. That's just showing the full zinc structure, and that some crystals, the chain comes in and out. It just depends what you take your data from. The last slide shows a mass of data on insulin from different crystals, and there are variations in the details of almost every structure. But I must leave it there today and say there's such a lot more of work suggested by these very random experiments that we should have more thought.